So at the end of the last class, we should have taken these notes on page 219, workbook page 219. Regular polygon means two things, equilateral, equiangular. However, if you have one, that doesn't necessarily mean you have the other. But if you got regular, you know for sure that it's both. And the thing that we're going to be focusing on about these regular polygons is the area, is finding their area. Regular polygons have a unique formula that we can use to solve for the area. And that is this. Area equals 1/2 times lowercase a stands for apothem, and the capital P stands for the perimeter of that regular polygon. Now, apothem, that length, we defined it and we said that the apothem of a regular polygon is the distance from the center straight down, perpendicular to one of the sides. So I guess it doesn't have to go down necessarily. You can go up and over to one side if you want, but it is the perpendicular distance from the center to a side. So the number of apothems a polygon has is dictated by however many sides there are. If there's 5 sides, then you can go from the center to those 5 sides only 5 times, as long as you're talking about the perpendicular distance. Some teachers, some professors will pronounce that word apothem. I've heard it both ways. Apothem, apothem, are notes to people that are gung-ho on saying apothem. I don't know. I like apothem. I think it sounds better than some toothless hick trying to say possum. So that's, I don't know. Apothem just sounds more proper, I guess. I don't know. Anyways, so this is what we wrote down. We said it's the distance from the center of the regular polygon to any side of that regular polygon, but it must be the perpendicular. Put that in all big caps. You must know you're talking about that perpendicular distance. And that goes for any time you're finding the distance from a point to some geometric object. You must be talking about that perpendicular distance. Well, these regular polygons, as long as it's regular, it can be inscribed in a circle, as long as it's regular. So all of these shapes that we're going to be dealing with in the next unit can be inscribed in a regular, in a circle. So, let's do this. Okay. This is the best I can do at a regular hexagon inscribed in a circle. If the polygon is inscribed, that means every single vertex of that polygon is on the circle. Just like when we talk about inscribed angles, I looked at the measure of its intercepted arc. We said, well, if it's inscribed angle, that means its vertex is on the circle. So this is an inscribed hexagon. And I did my best to make it look like it was regular. Really quickly drawn that. But if it's regular, equiangular, and equilateral. So the center of that circle is the same exact point where the center of the regular polygon is. That point is the exact same for the circle and that regular polygon. So this apothem that we've been discussing, there are 6 of them for this 6-sided figure. But just to draw one, that's an example of an apothem, and it will be perpendicular. We'll discuss more about that in a second. There's also another special segment that we wrote down last class, and it was the radius. These regular polygons have radii, and we wrote down in our notes that the radius of these regular polygons is it's a geometric object. It's a segment that connects the center of that regular polygon to any of the vertices. So once again, just like apothems, the number of radii for the regular polygon is dictated by how many sides there are. Because a polygon has the same number of vertices as it does sides. So for this hexagon that I've just made up and drawn, it has 6 apothems and 6 radii that I could draw in. The circle has infinitely many radii, but only 6 of the vertices are on that circle. And so, since this is an inscribed inscribed hexagon, it makes sense that the radius is from the center to that vertex, because the vertex is on. So that's why we call this length, that geometric object, that segment, the radii. Then we talked about this central angle of a regular polygon that's created by 2 consecutive radii. Maybe I just said radii twice, I don't know what just happened. Anyways, central angle of a regular polygon is created by 2 consecutive, very important consecutive radii. And it's going to open up to one side of that polygon. And so the reason this is so important is this is the very first step of us finding the area of these regular polygons, is that we've got to focus on this central angle. It's easy to find this measure because there's going to be 6 of these central angles, because there are 6 sides. So one of them is opening up perfectly to one side, because the consecutive radii go from vertex to vertex. Well, then however many number of sides there are, that's how many of those central angles there's going to be. So when we look at those 2 consecutive radii, and then this being a whole side length, I've just taken one of these triangles, one of these chunks, and taken out, like, I can find the measure of that angle by taking 360 degrees, the entire circle, divided by the number of sides. That's how many of these central angles there will be. So that whole circle, that whole 360 degrees is being broken up into, right now, 1, 2, 3, 4, 5, 6. And so since n is equal to 6, we can figure out what one of those angle measurements is, and in this case it would be 60 degrees. So, that central angle that's being created by 2 consecutive radii is 60 degrees. We're going to then focus on this triangle. What kind of triangle is this?
Isosceles.
It's isosceles, because all radii in the same circle, or in the same regular polygon for that matter, are congruent. So we know that those 2 sides are congruent. Well, if we look back at the area of a regular polygon, it says 1/2 times apothem times perimeter. We need to determine the apothem's length. We need to determine the perimeter of this regular polygon. Well, the apothem is the distance from the center of this polygon, and it's perpendicular to that side. So I can draw in an apothem right here. I can draw in an apothem. Think back in previous units and sections. If I had a triangle and I just drew in that perpendicular segment, what did we refer to that perpendicular segment in a triangle? Alec?
Altitude.
An altitude. Okay, and so that is the height. And we've solved many problems like this. It was on quizzes, it was on tests, where I gave you the 3 side lengths of an isosceles triangle. I mean, you draw this diagram, and you had to find the area. So you had to draw in the height, which was one of the altitudes that came from that vertex angle. And we proved, we did it together in class one day, and I also had you prove it on another quiz or test. What happens in this scenario? If it's an isosceles triangle and you draw in the altitude from that vertex angle, it breaks it up into 2 congruent right triangles. And you can prove that by hypotenuse leg. These 2 right triangles that are side by side inside this isosceles, they share a leg, the altitude, the height. So by the reflexive property of congruence, it's congruent to itself. But then you were told it's isosceles. So they have the hypotenuse congruence. So by HL, those two triangles are congruent. So when you draw in that altitude and that isosceles triangle from the vertex angle, it creates two congruent right triangles, and it will bisect that side length. Because if these two triangles are congruent, then by CPCTC, these two segments have to be congruent. And we already know that by the base angle theorem, or the isosceles triangle theorem, that those angles are congruent. By CPCTC again, I know that this angle up here is congruent, that it's being bisected because those two parts are congruent to one another. So we've looked at this situation before. So we're just taking that all that old stuff about isosceles triangles and altitudes and yada 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 and applying it to this. So once we have this, I know that this central angle created by two consecutive radii, I can quickly find that. 360 degrees divided by however many sides there are. So this whole angle, for this example, is 60 degrees. Then, we need to turn our attention to the right triangle. That's created by one radius, the apothem, and how can I represent this leg of the right triangle? It's half of the side. It's half of the side length. We're going to turn our attention to this right triangle because we know how to solve right triangles. We have a bunch of tricks up our sleeves. We've got Pythagorean's theorem that always works for right triangles. We've got our special rights, our 30, 60, 90s, and our 45, 45, 90s. And then we've got, if all else fails, trigonometry that we can use. So if we can get to this right triangle and solve it, I'll have my apothem's length, and then I can solve for half of my side, double it to get my entire side, and then just multiply it by however many there are in this regular polygon, because it's regular, meaning it's equilateral. So if you find one side, you've found them all, and then you can just add however many there are to it. Or multiply however many sides there are. How am I going to figure out what this angle is, though? I can divide the central angle by 2. Because this central angle created by the two radii, we can find that, 360 divided by however many sides there are. But then when you introduce this altitude, the apothem of the regular polygon, then we know that that bisects that central angle. So for this example with the hexagon, it was 60 degrees. So if I half that, I'll get 30 degrees. And so I could give you any one of these three sides, and you should be able to tell me the other two. So let's pretend that I gave you the radius was 10. I just made that up out of the blue. Well, you can tell me what my other sides are by using the 30, 60, 90 extended ratio. This is length of the short leg, length of the short leg times square root of 3, length of the short leg times 2. These are the extended ratio that it follows. Well, my hypotenuse was 10. That was given to me. So divide by 2 to find the length of my short leg. I get 5. Then multiply that by the square root of 3 to get my long leg, the side that's opposite the 60-degree angle, by square roots of 3. So half of my side length is equal to what? What is it? 5? So what is my whole side length equal to? 10? Because if half of it's 5, then 1 is 10. What's my perimeter then? It would be 60 units. Then my apothem length, 5 square roots of 3. So I can take these two values, plug them into that formula. So this is just the process of how we're going to go about finding the area of these regular polygons. It's not always going to be a 30, 60, 90 triangle. This only happens in hexagons and regular triangles. It only happens in regular hexagons and regular triangles. Well, it turned into a 30, 60, 90 triangle.